talk today about an original application of distance geometry in machine learning, and more precisely in unsupervised learning. So this is a joint work with Douglas Gonçalves from the Universidad Federal de Santa Catarina and also Leo Liberty. But first of all, let me give a bit of context and motivations of the use for such, or at least the connections between distance geometry and unsupervised learning. So, as you may know, many machine learning algorithms rely on vectoral input for several reasons. Some of them are due to the fact that the convolutional neural network have shown great performance on images. So vectoral inputs is always welcome in the case of supervised learning algorithms. And a variety of natural language processing or protein sequence representations are constructed with word embeddings, which are vectors in which are Euclidean vectors, to be more precise. And the constructions of these representations most of the time rely on an unconstrained minimization of a loss function using stochastic gradient descent. So we can suppose that we are given a finite vocabulary indexed by 1 until n, and we will call static embeddings functions which maps points of this vocabulary into a subset of RD, where D is usually much lower than n, and contextual embeddings, which appeared very recently within the deep learning community, which are rather functions over the set of sequences, or what we can call the monoid V star, engendered by the vocabulary. So here the dimension is not negligible with respect to n. These word embeddings naturally intervene, as I was saying, in natural processing or bioinformatic tasks, since proteins can be seen also as a sequence of k-mers. So in this presentation, I will discuss some aspects of current work. So first, new embedding methods based on distance geometry. I will present two algorithms which are, for the main part, very well known by the community in distance geometry. But I will show that the complexity of these two algorithms are better than the state-of-the-art embedding algorithms. And finally, I will present experimental results for classification and regression tasks in NLP and bioinformatics. So I will just recall the distance geometry problem, or DGP. If you're given an input as input an integer k, of course different from 0 and positive, a simple undirected graph, and a function weighting the arcs of your graph. The problem is to find a map, or what we can call an embedding in our case, such that the distance between the nodes are exactly the distances you have as input. And we call a solution of this problem a valid realization. So of course, this problem is NP-out in the general case, but when you have all the distances, it boils down basically to a matrix factorization. So this is of course well known. Also I can remark that it's equivalent to work with grammatices due to a transformation between the space of symmetric centered matrices to the space of symmetric null diagonal matrices. So this is just for reminders. And also, in some cases, the complexity is better than N3, which corresponds to matrix factorization. In the case where the graph admits a vertex order, such that the first m, so where m is larger or equal to k plus 1 vertices form a clique, and such that for all others, each vertex I has at least k plus 1 adjacent predecessors. Then we can find a solution in linear time. So I will present the geometric build-up algorithm with fixed references, which allow to obtain an embedding algorithm with better complexity than the traditional embedding methods in machine learning. So the idea of geometric build-up is to realize the first n vertices of the vertex ordering that we suppose we have. So we always work here with the assumption that previous vertex order exists. So we realize first the n vertices. We're using matrix factorization. This is a constant cost paid at the beginning of the algorithm, and then since it is equivalent to work with the distance with the scalar product, then the distances in our case, we will look at the local systems for all vertices after the initial n and transform them into local systems, and then see that these local systems are equivalent to a linear systems of a known x, which is equal to vi, and where a columns are exactly the reference or some predecessors in the vertex ordering. And the trick here is to, in order to reduce the computational complexity of this, or for the solving of all these systems, is to consider the same set of references v1 until v delta I, such that we can triangularize the system only once. And based on the assumption that we can choose the references as the first k+1 points, we then will realize k+1 references solving local DGP, so it can be with matrix factorization in this case. And then we will triangularize only once A, so the matrix of references, and then for every remaining vertex, we will solve triangular linear systems of the form AX equal BI. So this is a very efficient algorithm that I will show behave very well compared with other embeddings methods. So a second algorithm that I will present very quickly is one that we call divide and conquer. So the idea is to consider submatrices centered along the diagonal and forget some terms that do not appear outside of these submatrices. And the idea of the divide phase is to solve subsystems corresponding to each matrix, realize those points, and then with the intersections of those matrices, we will align the points obtained from one system to the points of the second system. And to do that in dimension k, you need at least k+1 points in order to define only one transformation from one set of points to the other. So the conquer phase will consist in solving sequentially all of these subproblems is done in the divide phase, and then from subinstance I to I+1, we will align those points, for instance, using Procrustes analysis. Which is of course solved, and there is no difficulty about aligning those points. So this is only about distant geometry, but now how can we use these two ideas in the case of unsupervised learning to construct word embeddings? So in the ideal case, we would like to have a distance between words or symbols that would measure their semantic difference. Using distant geometry methods, such a distance would yield a property such that two words would be semantically correlated if their corresponding vector are close. But here, a potential obstacle to this property would that the distance verifying the property A may not satisfy the traditional distance axiom in Euclidean geometry. But so in order to come up with a distance, we will instead of proposing an explicit distance, we will rather interpret the probability of co-occurrence of words within a context as drawn from a distribution that will depend on the scalar product of the word vectors. So this is actually one of the models for natural language processing. So for instance, here, the joint probability represents the probability of finding word I and J within a context, a fixed context window in a corpus, and Pi and Pj are the marginals of the words I and J. And here the assumption is to suppose that this quantity, well, the joint distribution depends on the marginals and the scalar product with this formula. I can give more explanation later for the choice of this expression. And based on this this model, one can derive a quantity which is called the Pointwise Mutual Information as an inner product approximation. And this quantity, this statistical quantity, can be measured over a large corpus of documents and estimating the scalar product. So now that we have an estimation of a scalar product or a distance, we can use the paradigm of distance geometry to solve the corresponding problem to construct word embeddings. And we conducted a very precise evaluation of the theoretical computational complexity of the most popular method versus our methods. And we were able to derive these expressions where you have lots of constants involved, for instance, the dimension of the problem, the number of references, but also the number of iterations required in the considered algorithm. So it is quite difficult to compare these values since or at least from this table, because basically you don't know in advance what the values are. But if you consider a concrete case, so for instance, a corpus of documents composed of about 300 million words or tokens with a vocabulary of 100,000 words, and you want to embed your words in dimension 50 with 200 references for the GBU, so the geometric builder algorithm, and the number of epochs is a parameter for the stochastic optimization scheme, equals to 15. Then you're able to compare the complexity of the geometric build-up algorithm versus, for instance, GLOVE, which is one of the state-of-the-art method for unsupervised learning of word embeddings. And it turns out that the theoretical factor is even smaller than 10, larger than 10, sorry. So we were able also to see that concretely, and I will show that later in the experiments. So concerning the experiments for natural language processing in the first part and for bioinformatics in the second part, we consider a corpus of 1 million documents from Wikipedia that we pre-processed following standard procedures. And then we evaluate these embeddings with two methods. So an intrinsic evaluation using human annotated semantic tasks, but also extrinsic tasks such as text classification. And we also compared with a baseline of random word vectors from a standard Gaussian. So for concerning the intrinsic evaluation, the quality of our word vectors, for instance, GBU, offers much better than the random ones and quite close to the state of the art. Or the difference is not so significant. And concerning text classification, the GBU methods or DC methods is also very close, sometimes second, even one time first on several data sets for different dimensions. Here, this corresponds to text classification with a consider a window size of 10. So this is for natural language processing. We also conducted experiments in bioinformatics. So we constructed k-mer embeddings of proteins on a dataset UniProt composed of more than 500,000 protein sequences. And we used these embeddings on 2 regression tasks. Channel rhodopsin localization, which can be formulated as binary classification, and a task of thermostability regression which can be translated in regression, standard regression. So for the results we obtained, it turns out that the GBU methods, when compared to the original methods in the reference paper, is better than for instance, doc2vec, which is another embedding method. But perhaps most importantly, if we compare the computing times of all of these word embedding methods, it turns out that the geometric buildup gives solutions in about in less than 2 or 3 minutes, whereas the most popular word embeddings takes about an hour or even 2. So namely GLOV or fasttext. So at the left here, these are the computing times only to construct the representations, and on the right, the time to construct the representation and also to train the classifier. So the gain in time is very large, and this is a property that is that can be very important in the case where no embeddings are available and you want to train new word embeddings, for instance, in lower source languages or for tasks in bioinformatics where you don't have word embeddings. So as a conclusion, I presented 2 algorithms to solve the distance geometry problem, and we showed that they have a much better complexity than the traditional embedding methods. And they also have a close performance or better performance to the state-of-the-art methods. And the perspectives of for this work are also to construct contextual representations, so representations that would not only depend on the considered word, but also its context. And more generally, distance geometry seems a promising paradigm for representation learning because only a proportion of distances is required to obtain realizations. For instance, you require 2 of kn distances, where n is the number of objects. And there exists some scalable algorithm in several situations and a dedicated literature with theoretical guarantees. And finally, we also think that it would be very interesting to generalize geometric buildup and divide and conquer to other geometries, for instance, hyperbolic geometry, since, as I said during the presentation, the distances that we consider may not respect the Euclidean distance axioms, and this can be a problem when you want to fit representations to the distance you measure.